Hello, everyone. Welcome back. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have AAS Journal author Edgard Rivera-Valentín with us today. Hey, Ed.
Saludos. How are you doing?
I am doing very awesome on this April 21st of 2022 because spring is definitely in the air in Phoenix.
Finally, none of this cold stuff. I was tired of that.
Yeah. Where are you at?
I am in Houston, Texas, where it's nice and warm and humid. I don't know, everybody complains about it, but I am here for it. It is my type of weather.
We get some of that Gulf Coast moisture in Phoenix, usually around July, August, because it moves on up, right? And this is what gives Phoenix its monsoon season. So it's all that Gulf moisture that Houston gets all the time. Very cool. Very good. Awesome. Ed, what do you like to do for research?
Over the years, I've had to learn to find a good one word that describes the stuff I like to do. Because honestly, it's what pays the bills, right?
Okay.
I have to have a job, but people prefer a good word. And I found that the word is applied planetary science. I like to do things where I can see there being an implication for like planetary defense, planetary protection, or maybe helping us go up and explore a body. So maybe helping with in situ resource identification. Cool. So that's the planetary exploration aspect.
Very cool. Nice. I like that term, applied.
Right?
You're gonna build a planet here or something. It's great.
Yes.
Awesome.
I can do that. I mean, in a model, but I can do that.
Oh, well, I am easily pacified, I guess. Okay, and that is gonna bring us to this very lovely Planetary Science Journal article. It's open access, people. Go ahead and go get it for free. Arecibo, S-band radar characterization of local scale heterogeneities within Mercury's north polar deposits. And Ed, take us away.
So we've known for a while that Mercury has ice in its poles, both the North Pole and the South Pole, in regions we call permanently shadowed regions. So those are regions where it doesn't receive direct sunlight, and so it gets cold enough where water ice is stable. Wow. And we've done that since about 92 when Arecibo and Goldstone Solar System radar picked up these really bright deposits up there. Then we sent like Messenger up to them, and Messenger also got us even more data to say, yeah, these are likely water ice. Cool. But like the story of radar doesn't end there. Radar can tell us a lot more than just here's a pretty picture with something really bright coming from it, especially if you have like a mission like Messenger giving you another data product that you can tie together. So what we did in this paper is exactly that. We took some data from Messenger, tied it with radar to figure out what is actually leading to the scattering that we're seeing in the radar signal. Cool. And so this is a big team because it is a very multidisciplinary work. We have a geologist, we have several geologists on board, we have radar experts on board, we have messenger data experts on board, all to put all of this together to really, figure out what's happening at these polar deposits.
Beautiful. Beautiful.
And I'll mention, by the way, that this is part of a focus issue in the Planetary Science Journal, which is called Arecibo's Planetary Science. We are collecting work where Arecibo data, either radar or radio, was used in support of planetary science. We already have about 9 papers in the focus issue and several papers already under review that are still making their way through. So we expect this to be a large focus issue demonstrating the importance and value of Arecibo in planetary science.
Absolutely. And for those who are curious why he used the word we is because Ed is also a scientific editor for the Planetary Science Journal.
Ta-da!
So, but we're going on the science side of things today, but good to bring that up. Awesome.
Yeah. So to start off our story, I am going to super skip down to figure 1 of the paper, which is on page 4.
An image, beautiful. Okay.
Yeah, look at that pretty picture. So with radar, when you zap something, you get back what's called a delayed Doppler image. So in the x-axis, that's the Doppler part of things. So that's telling you the rotational aspect. And in the y-axis, that's the delay aspect. So that bright spot all the way at the top, that's the part that is closest to the observatory. As you move further away, you get into higher and higher latitudes. So you get higher or into deeper delay values, which are plotted here. So this is the type of product that you would typically get from a radar observation. This is a Mercury. This combines two different polarizations. So it's important to talk about what that word means. So in radar, we transmit circularly polarized light out into space. And then we receive both the opposite circular polarization and the same circular polarization. So that's what we call OC and SC. So as I'm talking through this, if you hear me say those two words, that's what I'm talking about. Okay. This data product, we added OC and SC up. So this is a total power data product.
Cool.
And there's a couple of features that you can note here. The first thing is all the way in the back of this image, there's a bunch of these really bright stuff. That really bright stuff, that's the radar bright features at the poles of Mercury. So you can tell like why they are super standout, because around it, it looks like a bunch of noise and then suddenly bam, we have something bright here, right? And so the question is, what is producing this? We think it is water ice, but notice that you start to see less and less like craters and things the deeper in this delayed Doppler image you go. Right, you can tell like there's craters right at the top, and then you start seeing less and less of them as you go deeper until like it's just a bunch of darkness, and then you get to the radar bright features. That's because the way radar scatters off of a surface depends on the incidence angle. And so right at the leading edge there at the subradar latitude, that incidence angle is 0, right, with respect to the normal. And then as you go further back into the planet, the incidence angle increases up to 80 some odd, 90 some odd degrees. The higher you go, the thing that is causing the scattering changes. So at lower incidence angles, it's likely the topography. So that's why you see these nice craters at the leading edge, because those radar facing slopes are now sending you all that radar scattered back. The further you go, it's transitions from that slope to what is in the regolith. Are we talking about these big particles, boulders, that type of stuff? And that's why, so if you go to about minus 30 hertz and about 4,000 microseconds,
boom.
There you go. That little bright stuff there, that is called Fontaine crater. Cool. It is a bright rayed crater on Mercury. And because it's bright rayed, you know it's young. Otherwise, space weathering would have weathered it back to the normal background color. If it's young, that means it's not only like the albedo needs to be weathered, it's also like all the big chunks that were thrown out during the impact, that also needs to be weathered back to smaller grains. That hasn't happened yet. Right. Because it hasn't happened yet, they're making all the radar come back to you. So they look like radar bright stuff. So that's an example of going from topography being the thing that is controlling radar to now the stuff in the regolith being the thing that controls radar. So by the time you get to the back, it's really like, what is the composition? What is the dielectric permittivity? What is the sizes of the stuff inside the regolith? Right. That's the main thing that's causing the scattering. But then if you like want to study that, you need to know the incidence angle really, really well, right?
Yes.
Luckily, Messenger got us really nice topography data.
Cool. Okay.
So Messenger got up there around like early 2000s. So it was well after we got all those initial images. So once Messenger got there and got us all these really great topographies, now it's time to, okay, let's revisit things with Messenger and start doing basically radar scattering modeling to figure out what is making the radar return there. Basically, what is the composition of these things and do they look different?
Yeah, cool.
Okay, but to do that, like that's a lot of math, it turns out, because this is delayed Doppler. This isn't a real map of Mercury. You have to transition, like convert this from delayed Doppler to actual latitude, longitude.
Yes.
That's a truckload of math and a truckload of like fitting in like the day you were observing, the time you were observing, where was Mercury, what was its phase. And that's all the math you see leading up to that. That's me explaining, all right, now I have to convert all of this over to what latitude, longitude is. And then I really only care about the poles. So let me put it in polar stereographic projection and now stare out the pretty picture. That's what all this stuff is. But that then leads us to figure 2.
Ooh, nice.
That pretty picture.
Backscatter.
See, so I do want to take like a second to go look at this, seriously look at this pretty picture, because this is Mercury's pole from Earth. Like, this isn't a spacecraft orbiting Mercury that took a really high resolution image. This is from Earth. We took this. I would still think that it's super awesome that we have this level of technology and get these beautiful images. So yeah, look at this pretty picture. Okay, so in this pretty picture, I've highlighted the 5 main craters over the North Pole, and the exact pole is pretty much right about at the tip of Tragvedottir. I hope I said that crater's name right. These craters here, when we zap them with Messenger's laser altimeter, we found that some of them have something really bright right at the surface. And when we zapped a few of the other craters, we found that they're actually much darker than any of the nearby craters, even the background terrain. So, and yet they have something that's radar bright. So if they're radar bright, they should have ice, but they look dark in laser, while some craters look really bright in laser and are radar bright. What's happening there? The idea is that it could be you have, there was ice and it started sublimating away and left this lag deposit basically on top. And that's what you're seeing. But if you have ice and it's sublimated away and leaves a lag deposit, that means that ice isn't that pure. It has to have a level of impurity that's really dark to actually be a lag deposit. So then the question we have is, that already tells me that there might be some compositional differences between these craters. There might be, you might have some of them that have much purer ice, others might have less, or we don't know, right? We want to investigate this. All right, now we get to the incidence angle. No, we don't. Oh, right. I don't even remember my own paper. So now we get to figure 3.
I can empathize. I understand. Oh, DB's okay. Very cool.
So,
oh, nice.
Pretty again. I like pretty things. So in this one, so when we look at radar data, you take these imagery and you do what's called a z-score normalization. So the pixels no longer tell you this is the albedo. They tell you this is 3 sigma, 5 sigma above the noise, right? So those radar bright features were X sigmas above noise. Sometimes in the past, when people have studied to try to find where these bright things are, they set a floor. They say anything below 3 sigma, we're going to call it black. Anything above it will then actually gradiate. But that might have you miss on some of the gradients in the bright features, because now you're like saying, oh, this one over here, I'm deleting those pixels for no real reason.
Other than threshold, right.
A threshold that you randomly chose.
Right, exactly.
Yeah, I don't, plus then you have to like, somebody else in the future, you're gonna have to explain it to them why, and if you're not around, you're not there to explain it to them. So instead, I like algorithms, and you let like a good math that you say, put figure in this, output equals this.
Yes.
And so what we did is called a DB scan, density-based spatial clustering in noise applications. Applications in noise, and not nah. So all that does is if you have data that you know it has some level of noise, but those pixels have some spatial coordinates to them, if you pass it through this algorithm, you can identify clusters that are statistically significant above noise, that this is likely real signal. Okay. Clusters of real signal. So we applied that algorithm, and we're able to then automatically identify what those radar bright features were, where they are. And in this figure, what it basically does is we take If it is a radar bright feature that was identified, we then map it on top of the messenger map product that shows where the permanently shadowed regions are. Here it's in cyan. And if cyan and only radar map on top of each other, that equals brick red, brick orange. And if it's only radar, that equals yellow. So you see that all of the radar bright features are on top of PSRs, which you'd expect, because otherwise you have like a hot place that has a bunch of ice, and that doesn't make sense. There are some like little yellow pixels there.
I had to look pretty close.
Right?
Yellow.
Yeah, it's
yellow. Where's the yellow? But they're right next to the red. They're right next to the red generally. Right?
Yeah. So those are at the outskirts of a PSR. So this is what I'm talking about. If you would have set a z-score floor, you wouldn't see this. Now, of course, like you can argue this is an artifact of the algorithm, don't trust this, blah, blah, blah. But it could be like a real gradient, right? Even if you have ice inside a PSR, you should expect that because there's also a thermal gradient, as you move outward out of that really cold place, the ice could just go a little bit deeper. But it's deep enough that now it's not super bright in radar, but it's still there that it might still be visible, right? So it could be that. It could be part of that gradient that we may have missed.
Oh, right. I would much rather know a potential gradient than not have any information at all.
Exactly, yeah.
You can debate the reality of it later, but at least there's potentially something there.
Yeah. I'm a big fan of not throwing away data. And this just keeps everything together through an algorithm.
Very cool. That's beautiful.
Right. Plus it also makes a pretty picture. Here though, we highlight specifically also two craters, Sabkota and Burka in green. And the reason we did that is those are two large craters with really large PSRs. So you'd expect a radar return from them because there should be ice in them, but there isn't. There's a bunch of these larger PSRs who don't have ice in them. And we're still trying to figure out why. Why aren't all the cold traps at the North Pole occupied with water ice? That could be a constraint for what actually produced the water. Our current idea is that there was a comet, it impacted Mercury, the water from the comet volatilized, it kept hopping around Mercury until it found these cold traps, and then they got settled down and accumulated there.
Okay.
And then if the cold traps aren't all occupied, that provides like a limit on, it was maybe this one comet, but it wasn't this big, or two comets, but they had to be this small in order to provide only enough that you don't fill everything up. And then, I don't know about you, but when I stare at this, there's also like, you see more orange on one side, and then you see a preference for cyan only on the other side of the map.
Asymmetry.
Yeah, there's an interesting asymmetry there. Now, for my radar campaign that I'm showing here, this was only over a week, so we didn't get the full hemispheric view. So you could argue, well, you just didn't see the ones in the back, and I'd buy that. However, like I mentioned, other people have done this. John Harmon led observations on Mercury back in the early 90s and did full hemispheric view, and he still saw the same thing. There was an asymmetry there. So if there's an asymmetry, that could be another piece of evidence for this comet, and it could tell you, well, the comet came from the direction somewhere between 270 and 0 degrees west, because that's where we're seeing the most of these brick oranges. And it likely didn't come from the direction between 90 and 180, because that's where we're seeing the most only cyans.
Got it. Yes.
That's still under debate of what made these, and that is out of scope of this paper. I'm just showing data.
Great.
But I'm just saying, it's cool.
It's very cool.
Right. So then now we identified that most of the radar stuff, radar bright features are in PSRs, but there's some yellow that is outside of them. So that might start telling you something about a potential gradient. So now let's actually put together the incidence angle map and start doing the scattering. So that's the next figure in this paper, figure 4. This one of my co-authors took all of the dates that I had observed Mercury, and then basically simulated, took the topography map that we have for Mercury and simulated, all right, from Arecibo, if I show light and that light hit this topography, what would be the incidence angle?
Yes.
So that's what you see here. It goes from 40 to about 85. It stops at 85 because once you go higher than that, it becomes, the radar penetration depth becomes shorter than the wavelength.
Oh.
So you're not actually like seeing anything. It's just poof. So that maps out in white, and anywhere really that was in general what we call radar shadow that the radar never hit is in white. So you see like even some of like that big crater Prokofiev has some white spots on its wall and the other ones. So that lets us know I shouldn't expect anything here. And in fact, if I take my radar map and I put it on top of this, it's really cool. So Prokofiev, if you look at the wall, it's like white, 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 then a sliver of, oh, I should see something, then again, white, white, white. Yeah. That sliver, that tail, like you could see it really nicely in the radar. Like once you zoom in, there's like a little tail coming out from Prokofiev. So, you know, the simulation worked really well. Oh no, Prokofiev. So that, move your cursor down.
Oh, I was on the wrong feature. Down, 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 down.
All right, so there, stop, and now move to the side towards the center of the figure. Yes, Prokofiev.
Yes.
Right there.
Yeah.
Yeah, so you see that there's a tail there where it was still colored and then a bunch of white stuff around it. So yeah, so that tail in radar, we actually see that tail and it's really cool. So we basically put the radar map on top of this, and now I have radar backscatter coefficients in both the OC and SC polarization and have incidence angle. Now we can actually just do a bunch of science on this. Now we can transition from here's a bunch of really nice images to now let's figure out what they're actually telling us.
Very good.
And that gets you to figure 5.
It does. Very nice. Okay. That's
all right.
Okay.
These are the products. This is we took all of the collated radar backscatter coefficients and incidence angles, plotted them up. In blue, it's the radar backscatter of only the radar bright features. And then in black, it's the radar backscatter of only the background terrain. Anything that DB scan procedure said, you're not a radar bright feature, but you're still rare, you're just not a real bright feature.
Right.
And then so for figure A and B, you see that there's like a flat response for the background terrain. Yes. In terms of incidence angle, it's just a nice little bloop. That's exactly what you would expect if it was just a basaltic type rock at receiving radar at these incidence angles. It should be a flat response. Okay. When you don't see a flat response, that's when you go, oh, there's something else is inside here besides like rock. And that's exactly what we see for the polar bright deposits. In blue, they're not flat. It looks like they have some sort of relationship. We know it's likely ice, so we kind of expected it. We also see them higher than the background. That's why they're bright features. Yeah. So we can use all this and fit scattering models to it. And I'm actually going to come back to figure C and D towards the end. Because to tell this story, we're going to use A and B and start fitting scattering models to it. Okay. So if you scroll down the page, you'll see like equation 7. And so that's one of the scattering models that we use. That one works really well for rocky surfaces. And there's another one later on in the paper, in the next page, equation 10, that works really well for if there's if it's not just rocky stuff, if there's ice mixed in. So for the background terrain, now if you, for the background terrain, we took the radar, we fit the scattering model, we then, you have to vary the slopes, what's called the RMS, and the dielectric permittivity. And so we end up having to find the best likely combination of those values that then results in the best fit to the data. And so that's figure 6, which is up.
Yep. There we go. Just getting to the equations you were mentioning there. Okay.
There we go. Yeah. So figure 6, part A, is the reduced chi-squared space fit for the background terrain. And so the alpha there, that's that RMS slope of the terrain. But what we care about is the dielectric values. The dielectric value for the background is about between 2 and 2.5 in this region. So let's make sure those numbers make sense. Well, first of all, if we observed Mercury in passive radio and tried to get a global dielectric value, you'd get about 2.2. If we look at the moon with radar and we look at where it's basaltic rock, you also get something about 2. Huh? So those two, this number for the background terrain, which we know is basaltic, makes sense. Perfect. So yay, this type of like modeling is working. So now I feel confident. I double checked my paranoia. I think science is working. The universe is making sense. So I feel comfortable enough to go and do this again, but now for only the bright features.
Okay.
Well, when we do it for the bright features, what we did is we broke it up into the really, really bright stuff, which is also where we're seeing what's called high circular polarization ratios. So as CPR is what we acronymize it. I can make up words. I have a PhD, it's totally fine. So if you take the ratio of the amount of power that came back in the SC, same circular polarization, over opposite circular polarization OC, that's what CPR is. Okay. So we took it for high CPR, that's B, and low CPR, that's C. Got it. Because we want to see, is there a difference? And it turns out that C parameter, which again is something about the particle sizes and whatnot, that C parameter is basically the same if you compare these two. What's changing is the dielectric value. Between B and C, it almost shifts to the side. Yes. So if you are in a high CPR, which is the figure B there, the high CPRs, it comes out to have a dielectric value of something between 3.3 and 4.5. Yeah. Mm-hmm. And then for C, the low CPRs, that one comes out to have a value of something about between 4 and 5. Uh-huh. Yes. So first of all, yes, I'm fully aware that there exists a finite non-zero probability given these statistics that they're actually the same number, right? Because they overlap. Those ranges overlap between what, 4 and 4.5. But there also is a possibility that the bright stuff is closer to 3 and the less bright stuff is closer to 5. And they're just, so we wanted, yeah, they're just a nice little gradient. There's a little bit more dark stuff or some type of impurity in the ice. In fact, if we use what's called a dielectric mixing models, and say, what if I do have ice and I throw in a bunch of basaltic rock in it? How much rock do I need to mix within the ice to give me these numbers? If you do that for the bright stuff with high CPR, you get that you need at least 3% impurities by volume to give you those numbers. And if you do the same type of trick for the darker bright stuff, you get that you need at least 20% by volume rocks inside of it. So it's looking like we have a story that there might be a gradient inside there, and we want to further explore this because the scattering is telling us that, yeah, this might work. Nice. So, right, I like it when like you stare at something and then like it starts actually to make sense. That makes me feel better. Sometimes you have to stare a long time. You do. And then you find out it's just a bug in your code and you're like, oh. I don't want it. No. Those are the worst days. I like it better when, but it's, eureka moment when it's science. So here we go. Yes, exactly, yeah. So to dig through the data a little bit better, we go over to figure 7. So now we have evidence that there might be a compositional difference in terms of like the amount of rocks in it. Let's take another look to see, like, is there a spatial correlation there that's telling you? Okay. So to do this, I did another algorithm. This one's called a k-means clustering, where you give it a bunch of data and it clusters it into groups that can be distinguishable from each other. Yes. Now, typically k-means can be supervised. So that means like you look at the data and you go, I think there's like 2 groups here. And then k-means divides it into those groups. It could also be unsupervised, which I prefer better because the moment you say supervised, that means humans are involved and humans have error everywhere. So like I try to avoid that. So this is unsupervised. The way it works, it just tries to maximize the distance between the groups and the dispersion within the group. It minimizes the dispersion within the group. So it's really like distinguishable data sets.
Makes sense.
One of the reasons to do this is when you get these really high resolution radar maps, if you see like one bright pixel and then the pixel next to it is a little bit less bright or darker, let's say one pixel is 1 and the other pixel is 2, are they statistically different from each other? We really can't tell because in terms of radar, the errors in these pixels are not the same. Because the error in radar really isn't normal. It's not Gaussian. It's weirder. So instead of being able to go, this pixel is brighter than this other one, if you group them and talk about them as a group, then you can say this group of pixels is more likely different than this other group of pixels. I'm a big fan of statistics. I just like, it makes my heart feel better. That's where that comes from.
No, I was just getting my physical picture straight. Okay, good.
Yeah. So now when you stare at this, instead of seeing like a grayscale where you have to go, is this actually different from this? We can go, okay, so when we look at let's go with Chesterton crater, which is, you can pick whichever 3 at the close to the pole that you like.
How about this?
Yeah, let's go down. You'll see that there's like a yellow spot right in close to the middle. And then after the yellows, around it, it's green. And from that, it goes to blues.
Yes.
It's a nice gradient. So you see it there, you see it with its neighbor craters. But when we look at the craters towards the south of it, the return is different. It's very muddled. It's like, there's a yellow pixel, then not. But then yes, maybe.
Blurb.
Yeah, blurped. Prokofiev is the real big blurpy for me. Like there's blurpy in the big deposit, and then like in the central peak, it's nice and bright and yellow, but like the big deposit, it's blurpy.
Blurpy.
Yeah. In the paper, we decided that the technical term for blurpy is muddled.
Thank you.
Yeah.
I don't think blurpy made it into this paper.
It could have.
But I like it.
Right? So when we did this type of clustering, we did it only over, this image is only over the SC polarization.
Okay.
But it turns out when we looked at the data closer, besides this being a gradient in SC, it's also a gradient in circular polarization ratio. And remember, I broke down my radar scattering model between high polarization ratios and low. So wherever you see yellows here, it's not only high SC, it's also high CPR. And the scattering told us that's where the purest ice is. Where you see greens and blues, those are medium SC, low CPRs, and then really unpure ice. So when you're staring at those 3 craters that go yellow, green, blue, it's really, really close to pure ice, less pure ice, less pure ice, less pure ice, in a beautiful gradient. And I don't expect the universe to ever work in such a like pretty way, but like it really works nicely for these craters. So that's one of the big discoveries of this. That's the heterogeneities that we found. Some craters have this nice gradient in water ice purity. Others are more muddled. It looks like maybe there was a process that, like impact cratering that gardened up all of the ice and threw it all over the place to muddle it up. Or maybe the crater's getting a lot of scattered light from different places. So it's not exactly super cold. It might have cold spots and hot spots.
Right. Okay. Yeah.
And
this cheese model.
Yeah. So to test this though, we do have great messenger data that we can start using. We didn't do it for this paper, but the big revelation for this is to say Bepi Colombo, who is getting to Mercury around 2025, if I were to be constructing like a science operation strategy for that mission, let's say when you go study the poles, compare and contrast Prokofiev with that muddled deposit and Chesterton with that other deposit, and really get at high resolution over the ones that we're saying has a gradient in it.
Right.
And to see, like, verify, is this truly a gradient? Is that what we're seeing here? The other aspect of this is when going back to the whole, a comet came in and was the likely source for all of this, right? In order to like figure out how big that comet was, people had to say, well, all of this ice is this purity, sum up all of the ice, and that gives me the comet. But I just told you not all of the ice is nice and pure. Some of it is a little bit dirtier. So there's actually less water ice than what we had thought. So that starts reconstraining what that likely comet looked like.
Or the mass.
Yes. Yeah. The other weird thing though is, remember that in these scattering models, it allowed for high dielectric values.
Yes.
So water ice is closer to 3 in terms of dielectric permittivity. Sure, pure basalt rock is about 8. And so that's why, like, if I mix enough 8 into 3, I can move it up to 5, right?
I want in between.
Yeah. But you're constrained by the fact that in order for this to be super bright at these high incidence angles, you need to allow the light of radar to go through the ice unhindered and then come back to you. If you have something like a basalt inside of this ice, when the light goes through, it's going to hit the basalt and the basalt's going to absorb it. So you're not going to have something super bright. So the more impurities you have, that means it shouldn't be that bright. We shouldn't be seeing it. So the other option is that these aren't just pure water ices. There might be something like ammonia. There might be some other volatile we haven't thought of. And to me, that kind of just makes sense because a comet isn't literally a snowball. Like, a comet has a bunch of other stuff mixed in it. So I would have expected this to have a mixture of different volatiles. And that could be causing those higher dielectric values. It doesn't have to be a bunch of basalt inside there.
Okay.
So there's wiggle room here for Bepi Colombo to get more data to tell us, is this a gradient in rockiness, or is this a gradient in volatility, the amount of the type of volatiles there?
Yep.
Yeah. But we also like need more experiments to constrain the dielectrics of these volatiles, especially for radar wavelengths. So one of the volatiles that has been considered for these deposits is something called coronine. When I did a huge literature search, the dielectric value I found was in a completely different wavelength, and it wasn't even close to S-band. So like, I don't know what its number is in S-band. I could not find that value in S-band. We need that number. Somebody should go in a lab and zap coronine at S-band wavelengths.
For astrophysics opportunity.
Yes.
Lab astrophysics.
Yes. All you lab people, get me data, more data.
Good.
So that is another outcome of this. We need more of these numbers to better simulate what could these be composed of. All right, and then the last thing is actually going backwards. So now we're going to go back to that figure 5.
Yeah. C and D. Still got to cover C and D. Okay.
Yeah.
C and D. I'm with you.
Okay, so remember at the beginning you asked me, what do I like to do? I said applied planetary science, because I like to help in exploration and stuff like that. Good. These 2 figures are my exploration help in this paper. When we go searching for ice on other worlds, so that when humans get there, they could use it as a resource. In terms of radar, we have typically used what is that circular polarization ratio. So if something has a really high CPR, and that's coming from some crater that has a PSR, permanently shadowed region, then we'd go, that might be ice. Let's go dig there and get that ice. However, there have been people who have modeled what the type of radar return we expect from buried ice, and they've warned us that they don't think CPR is the best to use for this. Okay. So I said, great, let's test it, because Mercury has the canonical water ice deposits. And look, figure C. The CPR of the radar bright features and the background, they're just on top of each other. Like, yeah, you can't use CPR. It's not good.
Yeah, no,
You could kind of tell like a little cluster there, but that's about it, really.
yeah.
Now, those same people that have done these models had said, instead of using CPR, which is the ratio that SC and OC, don't ratio them, look at them separately. So plot them separately. And that's what we did in D.
That's kind of good.
And if you notice in D, now you have background terrain, that little cone of black pixels at the bottom. And then you have the cloud of blue really separated from it, which is the polar bright feature. So there we can actually easily tell, yes, these are where the ice is, over there is not.
Yeah.
So the aid here is when we go searching for ice on the moon, where we have radar instrumentation, we have also observed the moon from Earth using Arecibo, Green Band, Goldstone. We have missions with radar there like Mini-RF, who's been getting this data. We can now let them know, yes, all these people modeled this who say it's better to break it apart. Turns out it works much better if you break it apart. So when you're looking for ice on the moon, do it this way. And that was my applied help in searching for ice on the moon with this paper. And that's the paper. Isn't it cool? We found stuff in Mercury. We have a lot of questions open, and we're hoping future lab experiments and Bepi Colombo can help answer them.
Well, that's a perfect trifecta there.
Right?
Ed, thank you so much for walking us through your very lovely PSJ article.
Thank you for inviting me. And remember, this is focus issue and it's open, so you can still submit your papers to the Arecibo Planetary Science focus issue.
Cool. So you touched on it a couple times in several different ways about how we what are our next steps here for resolving these issues around Mercury's pole and what's there, and how much of it and all that, from laboratory astrophysics opportunities to different modeling. So where do we go over the next 2 to 5 years? Are there other wavelengths that might be useful to add to the observations? Is there any theoretical modeling that can be done? When will Arecibo 2 be built? What happens over the next couple of years?
Right. So the first thing that happens over the next couple of years, the closer one, is Bepi Colombo will get up to Mercury in 2025 and start taking really high-res data. So that will better help to characterize these features. In terms of future radar and future telescopes, it would be great. Like, I'm a big fan of doing multi-wavelength radar. You can zap it. Before the collapse of Arecibo, you were able to zap something with S-band at Arecibo. You could also zap it with X-band at Goldstone and receive the radar returns at Arecibo. You had a different wavelength and you had a huge light bucket in my background here receiving it. So we were able to get really detailed images. But without this dish, if Goldstone transmits, we don't have a big enough light bucket to pick up the signal and the details over Mercury. So although we're getting information from a different wavelength, we're not able to make those pretty images you saw here and do all the statistics and the analysis I did. We really actually need another huge light bucket to pick up those signals to do the analysis. So 100%, we need a future Arecibo or an Arecibo-like instrument. And in fact, Tuesday, April 19th, the Planetary Science and Astrobiology Decadal Survey was released.
Oh, yes.
And it stated several times the importance and value of the Arecibo Observatory and its planetary radar program, and recommended that NASA and the NSF work together to figure out what should be the future of Arecibo and build the next instrumentation. So that will be the next steps.
Awesome. I'm definitely looking forward to that.
More radar.
Where is he though? Very cool. Thank you, Ed. Thank you so much. And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Ciao.